Hi everyone, this is exercise 2 from lecture 4, and here we're going to calculate the tensions in these two cords that are holding up this traffic light. Okay, they're anchored at the walls, and here they're joined together and they have a traffic light pulling them down from this point. Okay, considering everything about the point where they're joined, if we look there, we're going to have a tension off in one direction, which we'll call tension 1, and a tension over this way, and the traffic light will be causing a force downwards, and that is due to its weight. So we often call that FW, the force due to something's weight. I usually use the component method in everything I do, so that's going to be the first way I solve these questions, but you could use the graphical method, and I might give that one a go in a minute. Okay, if we're using the component method, we always have to have an x and a y. This way, well, there's that one. My positive x will be off this way to the right. My positive y will be up. Now, you could say positive y was down if you wanted to, and then all of the tensions and forces that I would find in that particular y direction would be negative where they're positive, or positive where they're negative. And you'll find that if you look at the answers, Sanjita will usually have positive y being downwards, because that's the way that gravity acts, and almost everything ends up falling down in the end. So she'll end up with positive answers, and if I've got something falling down, I'll end up with a negative answer. Let's draw these vectors on. I'll just pick a different color. My T1 vector from this point is pulling in that direction. It's trying to pull the traffic light towards this wall. Okay. If that's the case, I'm going to draw that in here, and this will be T1. My other cable is up here, okay, trying to pull the traffic light up, or providing a tension for the traffic light to stay up. So that one goes up in this direction, and T2. And I can draw at any given time, because I'm doing the component method, I probably want to, a line parallel to the x-axis, and this, actually I might draw it in. This here is the x component of T2. I should draw this one in while I'm here. This was the y component of T2. Yeah. The angle is given to us as the angle from this line at the top to this vector. So this here is given to us as 60 degrees, and I know that there is 90 degrees between the x-axis and the y-axis. So if I have the inside of a triangle angles add up to be 180 degrees. Okay, 60 plus 90 is 150 degrees there. So what's left over is 30 degrees in here. And I want to find whatever the angle is from the origin outwards. The last thing to draw on here is the amount of force pulling it downwards. Okay, that's the weight force, but I've been given a mass. So I can draw that in, and this is the force due to the weight. And from the previous question we did, F is equal to ma. Okay, mass times an acceleration. So my 50 kilograms goes in there, and my kilograms, and my acceleration is 9.81 meters per second squared, which is the gravity for Earth. And we get an answer, if we look on our calculators, of 50 times 9.81 of 490.5 newtons. I'll let that sink in for a moment. We don't have a negative sign here. Okay? The reason why we don't have a negative sign here is because this is a vector, and a vector has a length, and we can't measure a negative length. Okay? why we can say this is because the vector points in the direction that it represents. I've got 490.5 newtons in this direction, okay, which happens to be in a direction that is opposite to my y-axis. If I write this down in a table, and I'll show you that in a minute, it will have a negative sign because a table has to stand by itself. It has to show you, if it's the component table, it's got the x and y directions, it has to show you if it's in the direction of positive y or the direction of negative y. But here, the vector diagram shows the direction, this just shows the magnitude. Let's look at what this table looks like. I might move this down if I press all the right buttons. And then hopefully I'll do the graphical way over there. On our diagram, well, let's just work out our sides. So this is how I usually set up a table. I've got an x side, try and leave enough room, and a y side, and I often include a heading column over here. Let's straighten that line up a bit. Okay, I've got a column over here which is where I'll just write my magnitudes. Okay. Let's talk about T1 for starters. T1 is a magnitude I don't know, so that's just going to be T1. The component of T1 in the x direction, T1 in the x direction for me will be cos, and I always use my angle from the x axis towards the y-axis. Okay, I measure that way. In this diagram, it's from the x-axis anti-clockwise, but in other diagrams that you draw, it may flip around because x might be on the other side or y might be down the bottom. If you're going to do this just by rote, which is how I end up knowing this method, is it's always from the x-axis towards the y-axis is where I make my measurements of angles. And that lets me have x cos theta. The x component is given by cos theta, and the y component is given by sine theta. Now, T1 I don't know, it's still going to be T1, a variable that I don't know. Cos theta is going to become cos of the angle that T1 is away from the x-axis. And you can look at this two ways. One is that T1 is on the x-axis, so it hasn't moved and it's 0 degrees. Or, if you always want your vectors to move, you could say, well, it's not here. Oops, back too far. Okay, it's not here, it's not here, it's still going around, it's past 90, it's past 180 degrees. Okay, down here it would be past 180 degrees, it's not there, it's not here, it's past 270, it's actually on this line, which you could say is 360 degrees. Okay, and if you want to, you can, instead of writing 0 there, you could say it's 360 degrees in here. But you will get the same answer using 0 or 360 in there. And that answer will be that cos of 0 equals 1. Different color. Cos of 0 is equal to 1, although you wouldn't write that on yours, you would just work out what that value was, which will be 1 lot of T1. Okay, T1 sine theta, T1 sine 0 degrees, sine of 0 is 0, so the y component here would be 0. If you want this to be written a little more formally, you could say that T1x is equal to T1, T1y is equal to 0. And we can see that up here, T1 doesn't have anything in the y direction, it's only all in the x direction. Oh, I'm going to run out of room. This button. We'll see if that's far enough. Okay, let's do the same thing for T2. T2, I don't know. It will be T2 cos theta, and T2 sine theta. Okay, T2, again, we don't know, but we do know the angle. Cos of, to get up in the direction of T2, it's going to be 90 degrees, which would point upwards, but that takes us to T2y. We don't want that. We're looking for the direction to T2, which is 90 plus 30, which is 120 degrees. Okay, so this will be cos of 120 degrees and T2 sine of 120 degrees. Okay, which will still be a lot of T2, so T2 x equals cos of 120. Cos 120 is actually minus 0.5. So minus 0.5 lots of T2 and T2 y component is equal to sine of 120, sine 120, which is equal to, or I've got 0.866, which I know as, well, I used to know. I'll just write that down. No need to be too exact here. 8.66 lots of T2. Now, this T2 is just the magnitude of T2, and that's how much we're using for the y component. And can you see that when we took cos of 120, it told us it was in the minus x direction, which is why I like this method, measuring from the x-axis going anti-clockwise for our angles. You can of course just use trigonometry with 30 degrees in there and work out whether you're using sine or cos to work out either y or x. And that will vary depending on which angle you use, and you'll have to double check, is this a negative result or not? Finally, as we come down here, no, we're going to colour in again. No, it's fine there. Finally, we'll do our weight force calculation. So I'm going to run out of room again. But we can still see it on the page. Nope, that one. Our force due to weight, which we do have a number for, I like to write in here. 490.5. We could leave newtons with it. In the case that's in a different sized unit, you'd want to change that before you start using it in here, because this way you can just add up straight down the row. Our weight force is the magnitude of our weight force, and the x component is cos of theta. Our y component is our weight force sine of theta, and our theta for this one, okay, if our x direction is that way, we can either go in the wrong direction, either go down this way and say it's minus 90 degrees, although the minus wouldn't be there, but I'm just showing that to illustrate the point. Or we can go around the long way, which is going around 90, around 180, and around to 270. And he would have 270 degrees or minus 90 degrees. Both will give you the same answer down here. It depends if you only ever want to go from x towards y and around, or are quite happy to go backwards and say that you've got a minus angle. Let's come down here again. So let's say we've got 270, just in case most people want to do it that way. Our weight force is 490.5, and we're going to find cos of 270 degrees. And our answer to that one will be 490.5 cos of 270, which is 0. FW in the x-axis is 0 newtons. I'll just put that in brackets. Okay. which makes sense. The weight force is entirely in the y-axis. We can see it from our diagram, but this is just keeping with the pattern in case we don't know where our forces are, well, where they break down to be, and the pattern will show you where that is. Here we have 490.5 cos of 270 degrees, which will be, that should work out, oh, I was about to say that worked out to 1, but it doesn't. If we type that on our calculator, if we type out 490 sine of 270, because we've already done cos, I could see that I've made a mistake with my lovely table. 490.5 sine of 270 gives me minus 490. FW in the y direction is minus 490.5 because it goes in the opposite direction to our positive y axis direction. Okay, and this would be a complete table. I can tell you from here T1 would be in the positive x direction. If I redrew this very quickly, T1 would be, well, and I told you where x and y was. Okay, T1 would be in that direction with no y component. T2y would have a part of it in the x-axis in the opposite x direction. A larger part of it would be in the y-axis because that is larger and going up. So T2 would be made up of this, and then my weight force would be down here, and that would equal 490.5 newtons. Okay, all of this information is from this table, but we don't need that, but that's saying why we need to have negatives and positives in our table. The last thing that we're going to use our table for, as we come down here, is this light is not moving. Okay. The should do it at the top, but I don't have room. The light is not going to move. So the sum of my forces in the x direction, my sum of the forces in the y direction, each one of those directions need to be balanced. Okay, if they're unbalanced, there's an unbalanced force on it, which for any given mass will provide an acceleration in that direction. So due to equilibrium, or because it's in equilibrium, no, we're going to play this game, are we? Can I have my... I think it's because I rest on the tablet. Due to equilibrium, because it's a rest, because it's at rest, or you could say constant velocity or acceleration equals 0, a equals 0, therefore the sum of forces in the x-axis equals 0, and the sum of forces on the y-axis equals 0. Up here, let's just sum up these forces, because the sum of the forces in the x direction is this number plus this number plus this number. So I get T1 plus minus a half T2 plus 0 is equal to 0. And then I'm going, I'll leave that there for the moment. I can't solve that. It's got both T1 and T2 I don't know. So let's have a look at this side. Maybe we'll get an answer from one of the other dimensions. So here, my sum is made up of 0 plus 0.866 lots of T2. Lots of T2. And I just like to put plus signs between all of my figures. Minus 490, it helps me to avoid mistakes. Minus 490.5 newtons equals 0. Here there's only one thing I don't know, so I'm going to add 490 to both sides. 0.866 lots of T2 is equal to 490.5. T2, if I divide both sides by 8.66, will give me 490.5 divided by 0.866, which will equal 566.4 newtons, and it's not, well, it's not quite that accurate because I've only used 3 decimal places, or 3 significant figures over here, so this should really be rounded to 3 significant figures, which would be 5.66 newtons. But now that I know T2, I can use T2 over here. I'll rearrange it first. T1, add a half of T2 to both sides is equal to 0.5 lots of T2, which is 0.5 lots of 566, which is equal to 283 newtons. Oops, 83. Oh, I didn't want the color picker. 280. Apparently I've been redefined, so I'll just use this. 280. This one. 83 newtons. Okay, and those are my answers. T1 is equal to 283 newtons, and T2 equals 566 newtons. This isn't the answer to the y component of T2. Okay, we use the y component of T2 over here, but our definition was in terms of a full of the magnitude of T2. Okay, and our answer told us the magnitude of T2. Okay, using subscripts helps you avoid the mistake of thinking this was just the y component. Again, with T1, we have the definition of T1x is equal to T1. Our answer is in terms of T1, not just T1x or T1y, it is T1, that's our answer there. We'll pause the recording here and recover my pen, and then go through the component method.